Everyone. Thanks for attending this last webinar before the IFAC World Congress in Japan. So, as you know, this is a joint initiative between IFAC TC on nonlinear control system and the IEEE TC on nonlinear systems. So this webinar is, as you know already, it is organized by Claudia Califano, who is the Vice Chair for Education of IFAC TC, Bayu Wanardana, who is the Vice Chair for Publication of IFAC TC, and Andrea Serrani, who is the Chair of the IEEE TC on nonlinear system and control, sorry. And myself, I'm Christophe Prieur, this is my last meeting as the Chair of IFAC TC 2.3. And so today we have the great pleasure to have Alessandro Astolfi. So maybe I can share my screen. Let me see if I can do that. I have just a small, even if everyone knows Alessandro, but I can share it. I can share my screen. Can you see my slide? Yes? Yeah. Yeah, okay, great. So I don't want to first. So everyone from the IEEE TC and the IFAC TC has all information, all regular information about the webinar. But if you want to register directly to the webinar mailing list, there is a Google form, and you can ask to Bayu or to myself to have the link after the webinar if you want to share this link with colleagues around you. Okay. So Alessandro, everyone knows Alessandro, so I don't need to read his bio in full details. So I'm very happy to have him today with us. So Alessandro has no more than 2 PhDs, one in ETH in Zurich, Switzerland, close to the mountains here in the Alps, and also another PhD from the University of Roma La Sapienza. And in 96, and then since then he is working with at Imperial College in London, and he has been doing 5 years an associate professor in the same time in Milano, and then since 2005 he is now also a professor at University of Vergata in Roma, and also a professor in Imperial College in London. So, you know, everyone, we know the activities of research activities of Alessandro. Is working a lot on nonlinear control system, mathematical control theory, and control applications. And today, so Alessandro, you know, he's a great lecturer, and he wants to attract a lot of people, and with a very nice, curious title. So it is just when Pontryagin meets Bellman, that is a title, very original title, and the abstract you had already the opportunity to read the abstract. So maybe I can save the time and let us switch now to the presentation of Alessandro, if you agree. Okay, so I will stop sharing my slides, and if you agree, Alessandro, you can start sharing yours. Okay, thanks.
Yeah. Full screen. Right.
Yeah, nice. It works. Thanks.
Excellent. All right. Okay. Thanks a lot. Thanks a lot, Christophe, Claudia, Andrea, and Bayu for the nice invitation. It's a pleasure to see, well, to give this seminar and to see actually so many people are, you know, connecting to the seminar on different time zones. So I apologize for keeping you awake. As Christophe said, I always had a double life, and this probably is responsible for my lack of sleep, but you know, that is you know, a different story. Right, so it is, as I said, a pleasure to give this seminar, IFAC CSS web seminar on, and I would like to focus on you know, optimal control problem and some game theory problem, differential game theory problem. So this is actually based on a joint work with Mario Sassano and Tulasi Mirvaganam. They were both former PhD students, are currently faculty at the University of Rome at Imperial College London. Now, before we start, I always like to have a sort of historical perspective of what we are doing. I would like to point out a very interesting article, so the Cold War and the Maximum Principle of Optimal Control, which actually revisits, the very beginning of optimal control. And, you can see Bellman here to the right and Pontryagin to the left. Allegedly, they never met. And so we could really say that their work was completely independent, and they definitely addressed the, among other things, the optimal control problem from a different perspective. And, while there's been quite a lot of work to try to reinterpret, Bellman's principle using Pontryagin principle and the other way around, we're not trying to do this. We are trying to exploit both principles together in order to get an alternative understanding of optimal control problem. And we will see that these, in a certain sense, lead the way to understand how optimal controller can be numerically computed. Okay, so the motivation for this work are essentially, as I said, the exploitation of the interplay between Pontryagin minimum principle and Bellman principle of optimality. And I would like to understand how this interplay can be exploited in the classical optimal control scenario, but for differential games, but also for iterative learning control. Interestingly enough, we'll be able to characterize optimal feedback as fixed point of a special map, and we will see that this is very powerful implication. Now, on top of this, we will show that the underlying Hamiltonian system, which arises whenever you pose an optimal control problem, can be stabilized, externally stabilized, without destroying the structure of the invariant manifold of this Hamiltonian system. And again, this allows for the computation of approximate optimal control strategies in a robust way. And all of these provides a different insight on game theoretic problems and allows, again, deriving numerical reliable approximation for optimal strategy for differential games, considering Nash equilibrium strategies. Right, so what is the plan of this presentation? I will start with infinite horizon optimal control problem, and very slowly from the linear quadratic case to the general nonlinear control problem. We'll try to understand how the two principles can be exploited together to provide an interesting view, a different understanding of optimal control problem. We'll then move to finite horizon optimal control problems, and we will see that there are some issues and difficulties that we will have to counteract in this particular case, especially the fact that you end up with, as you all know, 2-point boundary value problems. We'll then move again back to the infinite horizon optimal control problem and introduce the notion of controlled hamiltonians and discuss a new way of doing policy iteration. And this is very useful because it will give us an interesting interpretation of differential games in terms of interconnection of Hamiltonian systems. And as I said, perhaps I should call them controlled Hamiltonian system, but will be more precise as we progress. Now, there will be quite a lot of equations on these slides, and I apologize for this. Equations are simply placeholders. I mean, we recognize object because we're familiar with some equations. So by all means, these equations are not the core of the presentation, but they are useful because they are representative of some concepts and ideas. I'm also aware that for optimal control problem, there are important issues of regularity, and there's quite a lot of technical assumptions that have to be done in order to make sure that everything fits together very well, but all of these are not stated. So we assume that everything is as regular as we need and all technical assumptions are satisfied. All right, so let's start now with the basic ingredient for the linear quadratic optimal control problem. So the whole idea, well, the basic ingredients are, a linear system, and then a quadratic cost function, the underlying algebraic Riccati equation, and the underlying Hamiltonian matrix. Now, interestingly enough, if we try to trace back, the history of optimal control, I would say that the first optimal control problem was solved over 2,000 years ago by Queen Dido, when actually she solved the isoperimetric problem exploiting Green's formula, actually Green's theorem, clearly without having any clue in terms of all these mathematical tools. But I think this is a very interesting historical perspective. Okay, so we're all familiar with this tool. Let's try to provide a graphical interpretation of this tool. So the whole idea is that, suppose that this is the X lambda space. So suppose that I start from some initial condition X0 x0, and I would like to characterize the optimal feedback, which I call k star. So I forward propagate the state along the optimal feedback, and so I get that the state evolves, using the exponential of a plus b k star. So this is the optimal closed loop system for some time t. Now, after some time t, I actually perform the lifting of this point in the x space into the extended x lambda space, and this lifting is actually achieved essentially multiplying the x component by the identity, and the lambda component is obtained multiplying by p star, which is the solution of the algebraic Vergata equation times x of t. So this actually generates a point which is on an invariant subspace on the underlying Hamiltonian system. And if I backward propagate by the same amount of time along the trajectory of the Hamiltonian system, so I have this element exponential of minus ht, and then I reach again this point in time. So the idea is that I forward propagate in time, I lift this point, I backward propagate in time, and then I project back. So if k star is the optimal solution, and p star is the if k star is the optimal feedback and p star is the stabilizing solution of the algebraic Vergata equation, then I go back to x0. So essentially this for operation, this loop that I've generated starts from the point x0 and gives me back the point x0. So x0 is a fixed point of this map. The interesting observation, and we'll come back to this in a few seconds, is that it doesn't really matter for how long I flow forward in time, and I need to flow backward in time for the same amount, but I can make this loop as tight or as large as I wish, right? All these maps which are parameterized by t, they have a fixed point at x0. Now, we will see that it is useful to do the loop in the other direction. So you can say that this loop is clockwise. Let's try to do this counterclockwise. So I pick an initial point x0, which is the initial state of the system, and suppose that they have the optimal costate lambda 0 star associated with the corresponding optimal closed loop system. Then I forward propagate along the trajectory of the Hamiltonian system. I project on the x space, and then I backward propagate along the trajectory of the optimal closed loop system. So if everything is optimal, so if lambda 0 star is p star x0, and if k star is the optimal feedback, then again I go back to x0. Now, the interesting observation is what happens if I start from a point which is not the optimal one, or for example, I don't propagate along the optimal closed loop system. Then you see that I have this sort of black loop where I start from the point x0 lambda 0, and I end up to x0 prime, and then in this case lambda 0 is equal to 0. So in a certain sense, this shaded area is a measure of the fact that the optimal path that I followed, the path that I follow is actually not optimal. So the size of this shaded area is a measure of non-optimality. And so what we would like to do, we would like to understand how to characterize k star and p star in such a way that this shaded area is actually equal to 0, because this tells us that p star and k star are actually the optimal solutions, the stabilizing solution of the algebraic Vergata equation, and the stabilizing feedback. Okay, so let's try to summarize this graphical interpretation with some, sort of equations that are, more familiar to us. So the optimal feedback gain and the solution of the Vergata equation have two important properties. The first one is that k star should be stabilizing. So a plus b k star should have all eigenvalues in the left half of the complex plane. And the second property is that I have a map, and this map I called gamma pk. So this map is parameterized in p and is parameterized in k, and I can formally write this map in this form. So whenever it is evaluated with parameter p equal p star, k equal k star, and for any t, then it has a fixed point at x0. Now, you can actually write this map in a slightly more compact form. So essentially, you see that I have the forward flow phi along the optimal closed loop system. So a plus b k star, if it's the optimal closed loop system, starting from point x0 for time t. Then I compose this backward with the flow of, the Hamiltonian system, and then I perform the projection. I, should then perform the lifting before doing the multiplication, before doing the the composition. Okay, so what we have actually is that this map here is a fixed point, and this may remind us of what typically you see, for example, when you try to study, to explain observability to undergraduate students, that if a function is identically constant, is not only constant for t equals 0, assuming it is analytic, then all its derivative at t equals 0 have to be equal to 0. So this means that I can actually write this gamma mapping for t equal to 0, and this doesn't give much information. It simply tells me that x0 is equal to x0. However, I then do a time derivative of this for t, and then I replace t equal to 0, and I need to obtain again a fixed point, and so on and so on. So it ends up that this process gives us a certain number of algebraic equations. So the optimal feedback gain and the solution of the Vergata equation are such that A plus bk star has to be a matrix with all eigenvalues in the left half of the complex plane, and the matrix P star has to satisfy all these algebraic equations. Now observe that I rely on Cayley-Hamilton theorem, and it's important to point this out at this stage because for nonlinear system we won't be able to do this. The other important observation is that by relying on Cayley-Hamilton theorem, we need to stop at at power 2n. And why do we stop at power 2n? Because the underlying system that we are dealing with is actually the Hamiltonian system, which is 2n dimensional. Now, this equation have actually a very interesting structure because they are polynomial in K star, but they're actually linear in P star. And when you try to solve Vergata equation, you end up with a quadratic equation in P star, and typically then you compute K star a posteriori. Now the advantage of having a polynomial parametrization in K star and the linear parametrization in P star is that you can implement some interesting optimization algorithm in order to solve this problem. So the way we actually would like to solve this problem using some optimization approach is simply to consider the norm of all these differences, and then we square them, and then we add all of them together. So if you perform this operation, you see that you have a function which is actually quadratic in P star. The interesting observation is that no matter whether your problem is an optimal control problem or, for example, is a robust H infinity type of problem, and we'll discuss this in a few minutes, then you end up with a quadratic function that has the quadratic term which is positive semi-definite, and under some simple structural assumption, this quadratic function, this x is actually positive definite. And then you have the linear term, and then you have the constant term, which are actually polynomial in K star. And also the W matrix is positive semi-definite. Now, if we consider the trace of this matrix and we try to minimize this trace, so J is the trace of the matrix and is our objective function, then we can actually solve this problem as a minimization problem. And so as an optimization problem, and we need to be very careful because we would like to do the optimization over the manifold of positive definite matrices. So you start from some P0 and some K, and you try to perform a minimization. For P, you should stay in the space of positive definite matrices. Right, so this construction actually works regardless of the fact that the underlying Vergata equation is the one associated with the optimal control problem or otherwise. So suppose, for example, that you have the classical H infinity type control problem, the state feedback, the state feedback or full information H infinity control problem for linear system. Now you obtain a Vergata equation which is very similar to the one of optimal control, but you have this additional term which is related to the presence of the disturbance of exogenous signal W. Now, the problem here is that you have the quadratic term which is indefinite. And so for those of you that are familiar with the Newton-Kleinman iteration, which is typically used to solve medium scale Vergata equation arising in the optimal control problem, this cannot be used anymore because this heavily relies on the fact that the quadratic term has the right sign. Now, for us, this doesn't really make any big difference because we can again define the optimal feedback. And in this case, it's an optimal feedback in terms of a stabilizing feedback and in terms of the worst case disturbance. So we need to define K1 star and K2 star such that this matrix has all eigenvalues in the left half of the complex plane. And then again, we have this map which is exactly the same as we had before. Now we need to forward propagate along the trajectories of the optimal closed loop system, where optimal means the best control and the worst disturbance. And then we have exactly the similar terms. So you see that we have linear equation in P's, possible polynomial equation in K, and we can again repeat the same process and define a cost function and minimize this cost function in order to find the optimal solution to this problem. Okay, so you see that this algebraic Vergata equation that cannot be solved using the Newton-Kleinman iteration is actually such that this mapping has a fixed point. And so again, we can use optimization method in order to solve this set of equations. So just to give you an idea, we can write some pseudocode to solve this optimization problem. And we actually have a complexity of this problem, which is fairly limited. So I'm not a big fan of complexity because they only give a crude measurement of how complex an algorithm is. However, you see here we have our objective function j, then we can compute the gradient with respect to p and with respect to kj. We need and then we perform the minimization using essentially the gradient algorithm with an Armillo line search, and you see that the log of j actually has this type of behavior. Interestingly enough, Kleinman iteration works very well for medium scale problem, for example, up to order 10 or even 50. But if you go much higher, then the complexity and the sort of the cost of Newton-Kleinman iteration becomes very, 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 the complexity increases significantly. In our case, the complexity of the algorithm is somewhat half of it in terms of the exponent that you get here. So it can handle much larger problems. Another interesting observation that we can make is that, again, for those of you familiar with Kleinman iteration, you typically start with a feedback K that is stabilizing, and then you solve a Lyapunov equation, and then you perform this iteration. So you need to start from a stabilizing feedback. Now, in our approach, we don't have to start with a stabilizing feedback. And, I'll give you a very simple example where essentially we have a scalar problem. So P is the solution of the algebraic Vergata equation, and K is the feedback. And so if we draw the level lines of the cost that I've just described, you see that we get two global minimizers for this function. So two local minimizers, sorry. One is an optimal solution, and the other one is the corresponding destabilizing solution. So the one associated with the destabilizing solution of the algebraic Vergata equation. And then if we consider the domain of attraction of a gradient algorithm, you see that there's a set of destabilizing feedback for which are the one in red, for which the iteration that we have described actually converges to the optimal solution. And, unfortunately, there is also a set of stabilizing feedback for which the optimal solution converges to the set of the destabilizing solution. So in a certain sense, stability doesn't play a big role in the convergence properties for this particular algorithm. And, one has to be very careful in how the minimization is actually performed. Okay, so this is sort of a general introduction of how these ideas can be exploited for linear systems. And as far as I can tell, once we have an understanding of this idea for linear system, moving to the nonlinear framework is not more complicated. It's just, you just get more complex equations. So we have, a nonlinear affine system. We have a quadratic cost, infinite horizon cost, the underlying Hamilton-Jacobi equation, and the Hamiltonian function. Together with the Hamiltonian function, we have the Hamiltonian system, which is obtained through the gradient of the Hamiltonian pre-multiplied by a skew-symmetric matrix. Now, the graphical interpretation is pretty much the same. So we start from the point x0 and suppose that I have available lambda 0 star, which is nothing else than the gradient of the optimal of the value function evaluated at x0. So this point is if I flow forward in time along the trajectory of the Hamiltonian system. This is an invariant manifold. So I flow for some time, and then I perform the projection on the x-axis. I flow backward in time along the optimal closed loop system where pi star is the optimal feedback, and I should go back again to the point x0. So if I interpret this as a mapping from x0 into x0 parameterized by lambda 0 star, if lambda 0 star is the right one, so it is the optimal initial co-state for the underlying Hamiltonian system, and if pi star is the optimal feedback, then I go back to x0. So again, I have a fixed point. Now, if I start from, if I have an error in my initial point lambda 0, and so I don't start from lambda 0 star, again, I can flow forward in time, project on the x-axis, I can flow backward in time, possibly not along the optimal closed loop system, and you see that I generate this gray region. Again, the size of this gray region provides us the size of, a measure of non-optimality of lambda 0 star and of lambda 0, sorry, and of the pi that we have used. Okay, so this can actually be formalized pretty much as in the case of linear systems. So the optimal feedback gain and the solution of the optimal co-state equation are such that we have a stability requirement and the fixed point requirement. And the fixed point requirement can actually be written simply in terms of composition of flows and projection operation. Now, interestingly enough, we can repeat, assuming that everything is analytic, exactly the same process as before. So we can replace t equals 0, then we differentiate with respect to time and replace t equal to 0, and so on and so on and so on. And then we end up with a set of algebraic equations. So we can use the differential operator DIF, which is defined in this way. While the structure of this equation is not particularly important, what is interesting is that starting from a point x0 and a point lambda 0, we can actually find a set of equations that have to be satisfied by essentially the let's say the optimal process. Now, the interesting observation here is that once we solve numerically all these equations, we can actually find accurate approximation of the optimal control law around a particular point without solving any partial differential equation. Okay, so this actually, this equation can actually be written in closed form. An additional interesting observation before we move forward is that we don't have at our disposal Cayley-Hamilton theorem. So in principle, we have infinitely many of these equations. And so we will have to truncate this series expansion at some point, and then we will need to consider these as, in our approximation error. Okay, so let's see how these moves or can be exploited in the case of finite horizon problem. So the real difference in the formulation of the problem is that they have this capital T up here, and so the problem itself is slightly more complicated. Now again, we have the so-called pre-minimized Hamiltonian function, and then the Hamiltonian system, and then we know that together with the initial state x0, we also have a boundary condition at time capital T for the co-state. And since I don't have any cost at time, any end cost on the problem, then lambda time capital T should be equal to 0. Now, clearly, if I have the solution, if I have the value function, then I may compute lambda 0 star as a function of x0, so the initial condition of the co-state, simply evaluating the gradient of the value function at t equals 0 and for x equal x0. But again, we don't want to use the value function in this type of computation. So let's see how we can actually exploit these ideas in the idea that we've just discussed in order to solve this particular problem. Right, before we do this, let's very briefly go back to what is the classical approach to the numerical solution of finite horizon optimal control problem. Invariably, any numerical approach relies on the solution of the underlying two-point boundary value problem. And so what it is typically done in any of these algorithms is to transcribe this two-point boundary value problem into a nonlinear programming problem with different type of discretization of the time interval and polynomial approximation approximation. Now, the disadvantage is that typically you end up with a very large scale nonlinear programming problem, and these are sparse problem. And, you know, while these algorithms are actually very efficient, they don't scale very well. So our objective is to compute or to approximate the optimal initial condition for the costate variable, so lambda 0, by solving a system of n algebraic equations. So we would like again to exploit this idea of fixed point in order to transform our problem into a problem of identifying a set of algebraic equations. Okay, so I believe we now know what are all the ingredients involved in this type of process. So I would like to be able to characterize lambda 0 star as a function of x0. And I know that, you know, lambda t is actually nothing else than, you know, the evaluation of the gradient of the value function along the trajectory of the optimal closed loop system. Now, this means that I can characterize lambda 0 with the property that there is a function lambda a, which is defined in the interval 0t, and this is not a great idea because I'm looking for the time being at a function of time, with the property that this function is 0 at time capital T, and then there is a fixed point of this iteration. So again, I have that, you know, there is a function of time here, so this is my optimal costate, essentially lambda a, and then there is a function of time. And this function of time should give back, you know, the x0 lambda 0 initial point. Now, the reason why this is clearly unsatisfactory is that we get t in this position and t in this position, which is what we had in the previous framework. So essentially, we were flowing forward in time, projecting, and then flowing backward in time. But we also have t in this position, and this is definitely something that we don't want to have. So how we can get rid of this? Well, the whole idea is okay, so this is essentially describing, you know, what I've just discussed. So the distance between, you know, the final point of this tree operation and the initial point is again a measure of non-optimality. Right, so in order to get rid of the fact that lambda is a function of time, we can now use an approximation, for example, a polynomial approximation of the optimal costate, and this is parameterized using lambda 0. So we can use the invariant, you know, with the fixed point characterization in order to write this expression. And now all these objects can actually be explicitly computed. What happens is that since we don't have Cayley-Hamilton theorem, and so we don't have any information on the structure of the optimal evolution of the costate, in principle, we need to let this sum, this formal sum, go up to infinity. And so, you know, it's not something that we would like to do in application. So the whole idea is that we need to be able to truncate the sum at some point. And actually, we can show that for every error epsilon, there is, you know, an order of truncation that give us satisfactory performance. So rather than formally stating this result, you can see the way this works, right? So this is the optimal costate lambda star, and the time interval is between 0 and 1. And you see that if I pick a quadratic approximation, essentially I'm a long way away. So I have the condition at the time t equal 1, the optimal costate is equal to 0, which is my boundary condition. And then as I increase k, I actually get closer and closer to the optimal solution. So you see that this is sort of approaching, you know, to an epsilon neighborhood as we increase k. Now you can actually do, you know, perform a much better type of analysis. So you can, in a certain sense, start from some initial condition, and then you can start performing minimization in various directions, so with the various components of the costate. And so this is a two-dimensional problem where we start from some initial condition, lambda 0, and then we perform an iteration in one direction, and then in the other direction is a sort of coordinate direction optimization method in order to satisfy the invariance condition. And then this converges actually to the optimal costate. You see that the distance between the optimal costate, lambda 0 star, and the optimal costate at iteration k with a degree kappa actually goes reasonably fast to 0. So you can actually improve this method of constructing the approximation using some optimization routine. All right, so Interestingly enough, there is no reason why we should really iterate on the co-state, right? So we know that there is a boundary condition at equal 0 on the state and the boundary condition at capital T on the co-state, and we have opted to keep x0 known and try to backpropagate lambda at time capital T, which is equal to 0, back to 0. But we can actually perform exactly the operation, the iteration in the opposite way. So the whole idea is that we can parameterize the optimal state in such a way that, again, these maps are now sort of flown in the opposite direction. So backward in time, and then we perform a projection, and then forward in time. And then we have that the point 0, don't forget that lambda times capital T has to be equal to 0, xt should be a fixed point. And clearly in this case, x at time capital T is not known, but what we have is that at xa at time capital T is equal to xt. And this is where you see that there is again a fixed point. So you can repeat all the discussion that we had before in this case. Now, the question is, why would you want to solve the problem in this sort of backward in time way rather than the forward in time way that you have just seen? The advantage of this formulation is that if you have constraint on the states, you can actually embed this constraint in the fixed time in the fixed point condition. So suppose that the state does have to evolve outside a certain region of the state space, then you can embed this condition into the characterization of the optimal state that you get through this fixed point equation. Okay, now after this, we'll try to go back to the infinite oriented optimal control problem, and I present here again the same ingredient that we've just discussed a few minutes ago, and I would like to introduce a new notion, which is the notion of controlled Hamiltonian. Now, we all know that the Hamiltonian matrix, under some standard assumption, has a split spectrum. So there are n stable, asymptotically stable eigenvalues and then unstable eigenvalues, and this is very strong properties of the Hamiltonian matrix, but actually is very bad when you want to perform integration of the Hamiltonian system, because you may encounter, small numerical errors can actually generate very large errors. Okay, so what we would like to do now, we would like pretty much to repeat what we have done in the previous part of this presentation, where essentially we perform a sort of iteration where you start from, say, a stabilizing feedback, what we now call a policy, and then we compute an associated solution of the Riccati equation, which is a solution of an Hamilton-Jacobi equation, and then we try to assess whether these are a fixed point of our characterization. If this is not fixed point, we improve the feedback, so we improve the policy and we repeat the iteration. Now, policy iteration is essentially, is very well known in application. In the case of linear quadratic regulator, is nothing else than the Kleinman iteration. And so we have two steps. The first one is what we call the policy evaluation. And so we need to provide an estimate of the value function. We use an estimate of the value function to provide an estimate of the feedback law. And the quality of this estimate is typically assessed using something that we call the Bellman error. This is what is called in reinforcement learning, for example. Now, the estimate of the value function is then also used to update the optimal feedback. And so that's why we improve our policy whenever we improve our estimate of the value function. So how do we do that? So we essentially need to define the Bellman error, which is defined on the basis of a pre-minimized Hamiltonian. And this is nothing else that, the Hamiltonian where we have the running cost and then the Lagrange, Lagrange multiplier times the differential constraint. And then what we observe that for all time, the pre-minimized Hamiltonian evaluated along the optimal closed loop system, along the optimal value function, which is the lambda as a function of time is the gradient of v, and along the optimal x of t has to be equal to 0. But this equal to 0 again is equal to 0 for all t, and this is very important because it's essentially an invariant condition. So I can actually define a Bellman error simply replacing the optimal feedback and the optimal value function with some approximation. Now, if these approximations are actually the right one, so if there is no error, then E of t is identically equal to 0 for all t. Otherwise, there is a non-zero error that in some sense we need to try to minimize. Now, The Bellman equation can be defined in several ways. For example, in integral reinforcement learning, there is an integral version of this, which is actually evaluated over a moving windows. So this is the classical way in which policy iteration is performed. So we would like to propose an alternative assumption which relies on the invariance property, which is suggested by this equation. So the idea is that the Hamiltonian function, as I said, evaluated with an approximation of the value function, provides sufficient information to characterize the value function at a single time instant. Now, the problem is that if you want to use this on the basis of the Hamiltonian system, you have a problem because the Hamiltonian system has an hyperbolic equilibrium point with a stable and an unstable manifold. And so this means that if you use an approximate value function, then the Bellman error may actually diverge exponentially. So let's see why this is the case. So suppose that I have an Hamiltonian system and NS is the stable manifold. Then suppose that I start on the stable manifold with a tiny little numerical error. So I know that this manifold is invariant. So if I want to forward propagate the corresponding trajectory, I remain on the manifold and I approach zero. However, if we zoom around zero, then we have that the unstable manifold actually plays a role, and you see that this trajectory is very close to zero, but actually doesn't really converge to zero, but tends exponentially to go away to zero because it's approaching the unstable manifold. Now, what really we would like to achieve is something different. So we would like to be able to start away from the invariant manifold, but we would like to make this invariant manifold exponentially attractive. And then once we are on this invariant manifold, we would like to be able to float and so to have that zero is an asymptotically stable equilibrium. So in a certain sense, we would like to modify the trajectory of the Hamiltonian system in such a way that the stable invariant manifold is not affected at all. So it's still an invariant manifold. So this, and the reason why we would like to do this is that, if you compute the Bellman error along the solution of the original Hamiltonian system, you have a trajectory which exponentially diverges. Okay, so how do we achieve this objective? Well, the whole idea is that, we try to obtain a stabilization mechanism for the stable manifold of the Hamiltonian system. So if I rewrite the Hamiltonian system, with the x component as, x dot equal f1 of x lambda, lambda dot is equal f2 of x and lambda, and then I have an invariant manifold, and this invariant manifold is internally stable and externally unstable. The question is now to try to understand if I'm able to control the Hamiltonian system. So if I'm able to add an input signal here, I don't want to add an input signal to the first equation because the first equation describes the underlying nonlinear system that we're trying to control. So I simply would like to modify the second equation in such a way that I have an invariant manifold which is exactly the same as before, but this is now externally stable. Well, this is actually not too difficult to do. You can compute in the explicit form, the feedback law that achieves this objective. And so we call this a controlled Hamiltonian system. It clearly doesn't have the classical properties of the Hamiltonian system in closed loop, but is in open loop, it is an Hamiltonian system with an external input. Now, the external input can actually be computed in closed form, and there are, some terms which are actually dictated by, the value function v. Keep in mind that this is not a very good, this is not a very good solution because it relies on the knowledge of the value function, but we'll discuss this issue in a few minutes. There is a tuning parameter sigma f, which describes the speed at which you approach the invariant manifold. And if you implement this feedback law, then you obtain that the original manifold remain invariant and it is locally, externally, exponentially stable. So if you initialize this system, at x0, some eta 0, which is not too far away to the optimal lambda star, then trajectory of this will converge towards the invariant manifold exponentially fast, and then you will follow the invariant manifold. Now, I use here a new state variable because this is not lambda anymore, right? So in a certain sense, it's a different state, and these two systems only share the structure of the stable invariant manifold. Okay, so if we go back to the previous analysis, to the previous graph, you see that we now have a robust mechanism to compute the optimal costate, because you start from any eta 0, and then this will exponentially converge towards the invariant manifold and then move along the invariant manifold. So the zero equilibrium now is locally exponentially stable, so you don't have this phenomenon that trajectories diverge exponentially to 0. What you actually have, you have that if the distance between eta 0 and the optimal costate is smaller than some value, let's say mu, then there is a t star such that their distance remains smaller. You know, for any epsilon, there is a t star such that the distance becomes smaller than epsilon for all t larger than t star. So in a certain sense, you can control how fast you reach this manifold and how far away you are from the optimal costate. Okay, so this suggests that we can actually perform a sort of complicated construction where, you know, you start from the underlying plant that you would like to control in an optimal way or an infinite horizon. And then we can typically have a type of architecture, which is what is called in learning. And so the policy iteration is the following. So you perform what is called episodic learning. So you pick an initial condition x0, and then you sort of let the system run for some time. It doesn't have to run for a very long time. We'll come back to this in a second. And then observe that your stabilizer now is the eta state of the system. So in a certain sense, I have here a dynamic stabilizer. Now, this dynamic stabilizer provides a sort of Bellman error. And so I can then evaluate this iteration on the basis of the Bellman error, and then I can improve the policy and construct a new stabilizer. Now, the advantage that I have is that this closed loop system is stable. And so if I have a good approximation of the optimal value function, I get a good approximation of the optimal feedback, and then I get convergence to the optimal solution. Now, how do you achieve this objective? Well, the simplest possible way of achieving this is using a sort of polynomial approximation for the value function. So you define the space of jets, and then you take, in the spirit of model-based policy iteration, a sort of quadratic function, which is, through a matrix theta, and then the C are actually, all the polynomial terms of the xi. And, you could actually use a single layer neural network with polynomial activation function in order to be able to find this parameter theta. Now, you end up controlling the Hamiltonian with an approximate controller, which actually preserves stability but not invariance. Stability is a much more robust property than invariance. And so with this approach, we can actually get a stabilizing controller because this is stabilizing by construction, but we may not have invariance of the stable invariant manifold of the underlying Hamiltonian system. So we can use the distance from invariance as a reward at each, as a measure of reward for each episodic learning. Observe that by nature of invariance, the signal doesn't have to be sufficiently rich, because invariant is a property, it's a very fragile property. It has to be satisfied for all t. And so this means that we don't have to have sufficiently rich signal. We don't need to have sufficiently long episodic learning. So to give you an idea, so I can actually try to minimize the cost, which is the distance from invariance, so it's defined through this expression, and then using this parameter theta. And the interesting observation is that the distance from invariance actually is, easily characterized, as you perform, the evolution along, the closed loop extended system is not an Hamiltonian system anymore. You may have a problem that this function is a multivalued function because the maximum function of time can be achieved at several points. Actually, the interesting observation is, since you're interested in invariance, you can actually cut this. You can make it shorter in time because, once you're invariant for a certain short time interval, you remain invariant for a longer one. So invariance, as I said, is a very fragile property, but is also very powerful because it lets you essentially deal with a function, in this particular case, which becomes single valued. All right, so we can see how fast this function is decaying using this sampling gradient method or matrix manifold that we have implemented. And you see that depending on the length of your episode where you perform the learning, you have different sort of speed of convergence of your policy iteration method. Another interesting observation is the role of the tuning parameter. So the tuning parameter can actually be used to improve the speed of convergence of the policy iteration method. Okay, now this is a third order example where the solid line represents the optimal co-state evolution, and you see that we have here a family of functions which is approaching the optimal co-state as k increasing, and this is only based on a very simple gradient minimization method. All right, so finally, I said, some games. Unfortunately, these are not the type of games which are particularly fun, but, these are still games. All right, so one way of interpreting optimal control problem is to look at an Hamiltonian system and to observe that the optimal strategy can be regarded as the output of this Hamiltonian system. So essentially, in the linear quadratic case, you get that the output is minus b transpose lambda. Now, if you have a two-player game, then you can have a look at what we call the single player system. And the difference is that all of a sudden, this Hamiltonian system has also an input, which is essentially the effect of the other player. And so a two-player game can actually be interpreted as the interconnection of two single player system, and where essentially the output of one goes into the input of the other and so on. So this is a classical sort of feedback loop type of interconnection. Now, the problem that you have pretty much as in the case of a Hamiltonian system is that this interconnection may not have a stable equilibrium point. So how do you deal with this? So if you're only interested in open loop Nash equilibrium strategy, then you can actually, first of all, observe that these are the output of this feedback interconnection port control Hamiltonian system. The problem is that this is a feedback interconnection with a positive sign in both ways. So you cannot exploit passivity theorem. And so the underlying energy function is not bounded from below. So the underlying by a manifold of the corresponding Hamiltonian system is actually externally unstable. But we now know how to fix this problem, so we can essentially approximate robust Nash equilibrium strategies simply considering this interconnection and considering controlled Hamiltonian. So we add this new control variable, V1 tilde and B1 tilde, and you see that we end up with a situation in which the original evolution of the optimal feedback, I mean, you can get approximation of these, and then this is exponentially diverging pretty much for the same phenomenon that we described below, or you can have a situation where the optimal feedback, the optimal Nash equilibrium strategy are actually converging because we have been able to transform the unstable Hamiltonian system into a stable system where the invariant manifold remains unchanged. Okay, so I would say this is all what I want to discuss, and I would say that we have taken with my co-worker an unconventional perspective of Pontryagin minimum principle and dynamic programming to provide an abstract characterization of optimal policies in terms of a fixed point or specific map. And then once you're able to characterize this in terms of fixed point, you can actually develop a certain number of interesting algorithms to give you either the optimal solution for the linear quadratic problem. It's worth observing that if you want to solve a large-scale linear quadratic optimal control problem, you cannot really rely on standard tools. So you need to use, dedicated algorithm to do this. Interestingly enough, the same characterization works also for nonlinear system, and so we have been able to characterize optimal strategy with algebraic equations. And this is the algebraic equation. So this is been exploited in in learning, in the study of the so-called policy iteration method, and in differential games. Okay, so I clearly would like to thank Mario and Tulasi for their work, and a list of my co-worker and PhD students. So, and thanks all of you for listening to this presentation.
Okay, thanks a lot, Alessandro, for the great and very inspiring presentations that you gave today. So we have a few questions from from the audience. So maybe Felipe, can you ask your question if you don't mind? Can you open your micro for that?
Yes, yes. I'm currently interested in how the kind of tools you worked on, Bellman and Pontryagin style optimal control theory, can be used to illuminate state estimation. Observers and deterministic Kalman filters. The reason being, these problems are at least as important as state feedback, but I think it's arguably less well understood, less didactic. The nonlinear cases are not that well developed. So do you have any thoughts? I'd be very
okay, that's a very, very, very good question. And I've asked this question myself so many times, right? So I fully agree. So we have tried to exploit this idea for sort of the dual, forgive me for using this word, problem of the state observation and the deterministic Kalman filter. And we have actually, I'm not saying we have failed, but we haven't got really anything very concrete to discuss or to present. So, and I think the main issue is really that, the lack of availability of the state, right? So you can write a lot of these, you can construct objects, but these objects will depend on the state of the system. And so the fact that you just measure the output makes the situation way more complex. So the short answer is, I fully agree with you. It is an extremely important problem, but we are struggling to push this perspective in that direction. So, and not for lack of trying, as a matter of fact. Perhaps it requires some additional imaginative step that we are missing. So, yeah, I would welcome any suggestion in this direction.
Thank you.
You're welcome.
Okay, thanks, Alessandro. So I guess that Bayou, if I'm right, Bayou has a question, no? Do you?
Yeah, okay, so maybe this is a bit silly questions. So your graphical representations on the interplay between the co-state and state variables are very insightful. But if we have, yes, that one. So, but if we have a state constraint, how can we imagine this? Is it still kind of a valid?
Well, if you have state, no, this is not valid anymore if you have a state constraint. So if you have a state constraint, you should really try to look at this type of problem here, right? Because, well, actually, yeah, so this formulation here can help, right? And this can actually work in finite horizon and finite horizon framework. But yeah, so if you have state constraint, the previous formulation gets more complicated, right? Because our characterization of the optimal, well, clearly the optimal feedback, even for linear quadratic problem, is not linear anymore, and the value function is not quadratic anymore. So you need to resort to a more general formulation. But the one on these slides will still work. So you simply need to identify an XA of T, which satisfies all your constraints. And that really, this is something we are currently working on.
Right. Okay, thanks, Alessandro.
Okay.
Excellent.
Is there any other question? I have a small question, maybe a very naive one. So when you have the picture, so it was before this slide, when you are dealing with linear infinity control, yeah. So you have this nice picture with two local minimizer, one unstable and one stable one.
Yes.
So I guess that So this picture is typically what you obtain with a trace cost function, no?
No, yes, we trace the trace cost function, and keep in mind that this is a scalar system, right? So this is like x dot equal.
So if you change the cost, of course, the local minimizer will change.
Oh no, the local minimizer are well, okay. So the cost has to be a cost on these zeros, essentially, right? So you want to make sure that these are all zeros. So the most naive way of doing this is simply to take this matrix transpose times itself. You add this to the next one, you add this to the next one, and so on and so on. So you can do more clever stuff, right? The reason why we're doing this is that this structure still retains the fact that the cost is actually quadratic in P. right?
Okay,
And so this is very useful. And this quadratic and this convex, because as a matter of fact, it's strictly convex because you can prove that under standard reachability and assumption, the X is positive definite. So the reason why we do this is precisely because of this, because there is this structure here. Clearly, then for each fixed K, you have these nice properties, but then, you know, for different, you know, as you change K, then you also change these. But and this quadratic term does not depend on K, right? Okay.
So you can probably consider other kind of
absolutely, we can consider our kind other type of cost.
Maybe H infinity gain. And, fine. Okay, great. And is there a way to penalize the local minimizer that is corresponding to unstable control? I mean, maybe you can penalize and be sure that we converge to.
Well, you clearly have these stability conditions. So, but
yes.
so you can add these conditions as you know, an additional term in your minimization.
Okay, nice. Okay, great. Thanks a lot.
Thanks.
Is there any other question? No? Do not hesitate. Huh? So we have still a few minutes. No? It's okay.
Yes, I have a question.
Hiroshi, yes.
Yeah.
Hi.
Kind of the time. Hi, the time is not optimal for me to keep my brain fresh enough to be able to catch up with very inspiring but difficult theoretical presentation. But my question can be three. And when you look at the nonlinear system, so you need to know where you need to determine how much terms you use. You need to stop the kind of expansion somewhere. And you mentioned that you are going to elaborate it.
Yes, so you know, if you stop this expansion, essentially what you're getting a polynomial approximation of your optimal feedback. And you know, the whole idea is that clearly this is not so you will get a state feedback. So that the advantage of this approach is that, you know, you will get a state feedback and you can get a polynomial approximation of the optimal state feedback. So what you have to do, you need to sort of implement this in a receding horizon way. So you start from some point x0, you solve this equation, and up to a certain order, you have this polynomial approximation of your optimal feedback, and then you can repeat this computation after a while. The other possibility is to patch together feedback that you obtain out of this, and we've also looked into that. So you create a grid and then you patch together polynomial approximation. It becomes a very complicated problem when you have a high dimensional system because of patching together the various regions where the approximation is defined. So the way we actually always implement this is using a receding horizon approach. So you try to solve very accurately this equation at your starting point, and then you use a feedback controller for a while, and then you sort of modify the coefficient of the polynomial approximation.
Okay, so that part can be difficult to catch up with, but that point would be very interesting and important to make these things work and very efficient.
I
think. Yeah, thank you.
Thanks.
Okay, so we do have a very positive comment from Emilia and from Felipe in the chat. So I don't know if there is any other question now. No, if there is no question, maybe we can thank Alessandro again for the great lecture, and hope to see you face to face soon. Okay, thanks a lot.
Thanks for the invitation. Thank you.
And see you later. Ciao. Thanks.
Bye.
Bye.
Thank you.